Welcome to Who's in STEM. I'm Ken Ono, your host and the STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics at UVA. Our goal is to evoke flights of imagination and wonder by showcasing the cornucopia of all that is STEM at UVA, the marvelous world of UVA science, technology, engineering, and mathematics. Now, STEM research, it's really extraordinary in its breadth. And today, billions and billions of dollars are spent on R&D in our universities and in industry. And news stories abound with exciting medical breakthroughs, advances in engineering, and the emergence of big data and AI. These achievements, the medical breakthroughs, the engineering, AI, these achievements are stuff of the 20th and 21st centuries. In contrast, math research has a much older history, where advances seem to come along at a glacial rate. Indeed, just think about the Pythagorean theorem, right? That's a squared plus b squared equals c squared, which dates to 500 BC. That simple equation continues to drive and inspire research today. How? Well, ancient Arab scholars gave us such equations, maybe not that one. The Greeks introduced their geometry, like Pythagoras, and many of the deepest open problems that we think about have their origin in those works. But I have to admit, the study of numbers, as old as that may seem to be, is not the oldest STEM field. And maybe it's not even close. You see, mankind has been enchanted with the sun, the moon, and the stars, the heavens, and that interest is basically almost as old as time. Right? Mankind has forever looked to the stars for guidance, for worship, and for navigation. We're constantly looking for patterns in the sky, right? Let me just mention the constellations, Aquarius, Cassiopeia, Ursa Major, right? Also known as the Big Dipper. The stars have told us mythological stories. And the allure of the stars continues today. Think Hubble telescope, space exploration, black holes, and so on. This is the stuff of NASA. What are STEM researchers doing? Well, they look to the sky for many reasons. They seek clues about the origin of the universe. They test Einstein's theories. They want to understand the nature of gravity. And they're even looking for evidence of extraterrestrial intelligence, right? Think SETI, made famous in the Jodie Foster film Contact. And if you didn't know it, I'm pleased to tell you that astronomy is booming here at UVA and in Charlottesville. UVA astronomers are award winners. They abound. NSF Career Awards, Packard Fellowships, and major NSF grants. Charlottesville is also home to the National Radio Astronomy Observatory headquarters, not far from grounds on Ivy Road. It's not an exaggeration to say that astronomy is red hot in the UVA universe. And today it's a pleasure to feature one of our star UVA astronomers. Ordinarily, you'd expect me to talk to, say, the chair of the astronomy department or a recent winner of a major prize. But today, it's a special privilege to speak with third-year undergraduate in the College of Arts and Sciences, Samuel Crowe. Sam has been in the news, and it is believed that he is the first undergraduate in NASA history to be named a Principal Investigator of a Webb telescope project. Sam, welcome to Who's in STEM.
Thank you for having me. I'm excited to be on the show.
Congratulations. Before we get to the Webb telescope and your project, tell us a bit about yourself.
Sure. First, thank you for the congratulations. So I'm from Southeast Virginia, from a little city called Chesapeake. I grew up with my mom. My mom, as you may know, has a PhD in mathematics. She got her PhD while she was raising us before she became a professor. So she taught at Norfolk State University for 13 years, and now she's actually moved to UVA to start last year in the Applied Math Department in the engineering school. So already I've had some STEM engagement from when I was very young from my mom. So I always kind of knew I wanted to do something in a STEM field, but it wasn't until I started high school I was a physics major, or not a physics major, but I studied a lot of physics in the International Baccalaureate program at my high school, and that was when it really clicked for me. I knew I wanted to study physics, and the love for astronomy that I'd always fostered from when I was very young. I'd always loved astronomy. I connected those two things together, and I said, okay, I want to be an astrophysicist.
So was it a high school teacher that piqued your interest, or it's the combination of your teachers and your mom?
It was definitely a combination of them. I had a very great high school physics teacher, and I think he was very formative in my decision to pursue physics. I also had a great history teacher, and as we'll discuss, that may have motivated my love for history as well.
Wow, I didn't know you were interested in physics, astronomy, and history. That's quite a broad set of interests. So Sam, with all of these interests, what are you studying here as a third-year student here at UVA, like this semester? What are your courses like?
Sure. So as a double major, I'm first of all majoring in astronomy, physics, and secondly majoring in history. I'm taking a lot of courses across astronomy, math, physics, and history. So in particular, this semester, I'm taking some upper-level physics courses, but I'm also completing my history capstone thesis on the Roman Empire.
So turning to the astronomy, because that's the big news here. Tell us, how did you first get involved in research here at UVA? Was it a class? Was there an astronomy professor that you really hit it off with? How did this all begin?
Yes, so it was actually a class. It was a course in the astronomy department that is essentially a one-credit course where professors just come and do research talks.
Wait, did you say a one-credit course?
One credit.
Oh,
yep.
amazing.
Yeah. Small course. So Professor Jonathan Tan, who's a research professor in the UVA Department of Astronomy, came and gave a talk sometime in February, my spring semester, first year. And me, being a first year, not really knowing what research was, I just thought, well, what he's talking about is very interesting. He was talking about star formation and these things that we'll be discussing with my research now. I thought, well, this is very interesting. And I just went up to him and asked, hey, do you have any research opportunities? And he said, yes, I do. So I started from
I love it when it works that way.
Yeah.
So what were these opportunities? So you're a first year, you're in a one-credit course. You approach Professor Tan at the end of class and asking for research opportunities. What happened next?
Well, it's somewhat of a long and continuous story, but I started a project with him that ultimately took me to Sweden to work with him over the summer.
So did this begin with a reading class or?
Well, we sort of jumped right into the research. I started with a project that motivated actually this James Webb program that we're talking about today. And that sort of led into this summer program that Professor Tan holds in Sweden every summer, where he takes some UVA students along with some other international students and sort of holds a summer school for doing research in Sweden. So I did that. And then ultimately, I've done other projects with Professor Tan. Last summer, I was in Spain working with one of his previous postdoctoral researchers. The research journey has continued, I think, with Professor Jonathan Tan since that first meeting, for sure.
So in Spain, was this work at an observatory? Is it theoretical work? What does that look like?
Well, so it's observational work, but maybe unlike what you might expect, observational work for an astronomer doesn't involve going out every night and looking through a telescope. Mm-hmm. So I was working with observational data, but it was all on my computer. So it's all coding. Really, it's all sitting behind a screen. Yeah, so I was working at an institute for astrophysics in Granada in Spain, working with an advisor, Dr. Ruben Fedriani, on a new project that was still under the umbrella, I suppose, of Professor Jonathan Tan's group. So I still met with him. He was still closely advising the project.
Did this work result in a paper? Have you presented it at a conference?
Yes, so actually I'm just now getting published a paper in a journal, Astronomy and Astrophysics, on the work I did in Spain. And besides the paper, I've also given talks internationally. So I've given talks in Spain. I went to conferences. There was one in Sweden. I went to one in Greece over the summer as well. I've also given talks in Seattle within the U.S. and New Orleans. And last September, I was invited to visit the University of Arizona in Tucson. So I've liked to think that beyond the research that I'm doing, another important part of it has been disseminating the results and getting people hopefully excited about what is the research that I'm doing.
So speaking of the research, so you're in demand. Tell us about it. What's the work about?
So we're primarily studying how massive stars form.
And a massive star is?
Usually over 8 times the mass of our sun.
Oh,
so you can imagine
big.
Our sun is really big. Over 99% of the mass of our solar system is in the sun. And these stars are even bigger. They're absolutely enormous. And they're sort of like the rock stars of the universe. So they live hard and they die young.
So they die young even though they're huge.
Yes, they may only live for a few millions of years, which may seem short in our human timescales, but in a cosmic timescale, it's actually a very short amount of time. So they're very important, as you may know, because they die in the form of supernova, which create heavy metals that populate the entire universe. That's the entire reason that I'm here right now speaking to you, is because of these heavy metals from massive stars. But even while they form, they have a very large impact on how galaxies evolve, how other low-mass stars form, and things like that. So they're a very, very important piece of our understanding of the universe.
So help me, how many massive stars have astronomers observed and studied? Hundreds, thousands? Just to give us a scope of the universe.
So really, I would say only a handful in terms of very close, deep observational studies. They're very difficult to study because they're usually further away, relatively speaking, than lower mass stars. And also they're usually surrounded by a lot of stuff, a lot of material that make it hard to peer in and actually see what's going on. So actually one of the big important pursuits in massive star formation right now with these big powerful observatories that are coming online is to characterize massive star forming regions in a lot of detail because we can finally do that. Right.
Okay. So if you discover a massive star, even one massive star, it's like a big deal.
Or if you can study it with a lot of detail with maybe different telescopes at different wavelengths, and you can say something about how in general massive stars form based on that one object, that's a very big deal.
So for us here on Earth, in our solar system with our not-so-massive star, what do you hope to learn in this research? Why does it matter?
Well, I think it matters a lot. Like I said before, these massive stars are informing a lot of our understanding of the flows of matter and energy in the universe. So, for example, if we want to understand how stars form in general, understanding how the massive stars form is very important to understanding that process. If we want to know how galaxies evolve, even going back to the very early universe, so the very origins of our universe, understanding how the most massive stars interacted with those forming galaxies, those first galaxies in the universe, is very important to understanding that process. So one of the reasons I like massive star formation is that it is sort of this all-encompassing process that can tell us a lot about the current state of the universe and a lot of different spatial scales. So down to the relatively small scales that we study close to our solar system to the biggest scales of the early universe and the formation of the first galaxies.
That's amazing. Thank you, Sam, for explaining that. Now, the Webb Research Project. So the Webb telescope is fairly recent, but as I understand, there are many different kinds of telescopes. From the mirror reflector telescopes that amateurs have. I had one as a kid growing up, the little white cardboard tube with the little mirror on the end. Radio telescopes. We've got the famous named telescopes like Hubble, Chandra, and now the Webb telescope, which I understand is just about 2 years old.
That's right, yeah.
You're now a member of the James Webb Telescope Program, and a very exclusive club. And as I understand, we believe and we're pretty sure that you're the first undergraduate to be a PI, a principal investigator leading an experiment with this telescope. But before we get to what that looks like, what distinguishes the Webb telescope from all of the others? Why is it so important?
Yeah, so it's important for a lot of reasons. I would say the primary reason is because of the wavelength. So, of course, light has different lengths of the light rays, and that determines usually in astronomy what you want to study and the things that you're looking for. So the Webb telescope is a near-infrared instrument. So infrared is longer than the wavelengths of light that our eyes can see, but not so much longer. It's maybe 4 to 5 times. It extends from the near-infrared all the way up to the mid-infrared, which may be 10 to 20 times the wavelength of what our eyes can see. And this is important for a lot of reasons. Actually, it was constructed originally to observe the earliest galaxies in the entire universe. So to discover more about the origins of our universe, because oftentimes the light from those objects will come to us in the infrared. It's also useful for studying star-forming regions. Like I said, these regions are covered in a lot of dense gas and dust and material that blocks the light coming to us in the visible light. So if you've ever seen images, for example, of the Milky Way, you know those dusty bands that usually cover much of the Milky Way. That's because it blocks visible light. But if you look at it in the infrared, you see right through all of that dust, and you can see all the intricate substructure and detail of star-forming regions. So the infrared is a key wavelength regime where we want to study how massive stars form.
Right. So it's not the first infrared telescope, but in terms of power, it's the most powerful by a factor of...
I would say by a factor of maybe 5 or 6
Got
above
it.
what the Hubble Space Telescope was able to do and other previous generation telescopes.
Right.
It also is incredibly sensitive and has incredibly advanced instrumentation on it that is basically pushing the forefront of what science and technology can do. So it's a totally world-class, one-of-a-kind telescope. There's never been one like it before, and it's totally revolutionizing our understanding of many fields of astronomy.
Right. So I remember, I'm much older, I'm in my 50s. I remember when the researchers that were working with the Hubble telescope were announcing and releasing these amazing images of regions like the Eagle Nebula, where you had these, and I think many listeners will be aware of the brilliant pictures, images of star and galaxy formations. The colors are beautiful, and it's really quite mesmerizing. And so I guess what you're telling us is that what the Webb telescope allows us to see today is that sort of image, but in much greater detail and further out in space. Would that be correct?
Yeah, of course, the Hubble's done a wonderful job, and it's still operational.
Right.
Amazingly, as a testament to its incredible power. But yes, the Webb telescope is at least a factor of a few times more powerful than the Hubble telescope. And actually, the James Webb has reobserved some of those famous regions the Hubble observed and showed us just how much more detailed it can be in terms of its observing power.
Okay, that's amazing because I was already very impressed, I think like everyone else, with the Hubble. Well, that has to be super exciting for you, Sam. So as the first undergraduate researcher to be granted PI status, and I want to clarify to the listeners that it's a big deal for you to be the first undergraduate researcher to be granted PI status. Full professors at Group 1 research universities are hoping to get this status. As an extraordinary research tool, people are clamoring for this opportunity. What does it mean to you to be the first?
Well, it's very meaningful to me, and I hope it's also meaningful to a lot of my friends or other people that I've met because as a student, like you say, the odds are sort of stacked against you to do this sort of thing.
Well, for everyone, I think it's something like only 1 in 3 proposals are accepted, maybe less.
1 in 7, yeah.
Oh, 1 in 7. Okay, I stand corrected.
It's much less. Yes, but I mean that for a student, of course, we lack the experience, maybe some of the expertise, some of the knowledge, and that puts a block, maybe more of a mental block of maybe I can't do this sort of thing. But I think that to me, to be able to have done something like this proves to me, and I hope also proves to other people in the field, for as students, that yes, you can do this sort of thing and that you are capable of doing this and that you can pursue your research ideas. So this is also research freedom, right? It's I have an idea and I can actually go test it because I have an idea that's worth consideration. 2
thoughts come to mind here. First of all, I want to hear about the process. As an undergraduate submitting a proposal to NASA, that seems pretty audacious. So what did it look like to you? What were you thinking when you were assembling this proposal? Were you thinking this is just good practice for writing a proposal? I mean, what were your thoughts?
That's actually exactly what I was thinking. I wasn't actually so concerned with the outcome, more so than the process of it, thinking, well, this will just be a good opportunity, if anything, to improve my writing skills and actually understand how this whole proposal writing and submitting process works. But yeah, it wasn't a very straightforward process. I mean, as you can imagine, I'm in my head about it this entire time thinking maybe I can't do this, maybe I don't have the skills and the knowledge necessary to do this. But it was just a process of just doing it without thinking about it so much. So writing things down onto the paper and seeing where it took me without having a fully fledged idea of what the final product would look like. And so it was a step-by-step process. And of course, I had a lot of help from my advisors. I didn't do it alone. I couldn't have.
Did they share with you samples of previous successful proposals? I mean, What kind of guidance did they offer? Were they cheering you on, saying, "Yeah, Sam, we think you can do it"? What did that look like?
There was a lot of support, but also in the proposal cycle, the group of Professor Tan was putting in a lot of other proposals. So it was, I get some attention and I get help, but also like there's 10 other proposals that also need to be polished at the same time. So for me, it was I'm one of many, and I'm going to sort of stay in the corner I've been allotted and work really hard at what I know I can do, which is to write something compelling and something that makes a good case.
Do you think your training as a historian helped you craft your proposal? Did that offer you any perspectives that would have been unique, you think, among the pool of proposals?
I think most definitely. I mean, ultimately what you're doing when you write a proposal like this is you're drafting an argument. I mean, you're saying, I have this idea, sure, but when you have a good idea, you still have to argue for why it should be worth consideration and carried out on. And so I think my experience writing papers for history courses, which are basically just taking facts and constructing an argument out of them, definitely helped prepare me and gave me the aptitude that I needed to be able to write in a scientific sense and to make this argument that was compelling enough to be accepted.
So when you heard the good news, did it come in a form of an email, a letter? What was going on through your mind when you heard the good news?
It did come in the form of an email.
Just an email?
Yeah, a relatively humble email in my inbox that says, "Congratulations, your program has been accepted." But I was absolutely thrilled. I mean, I called my mom first and told her, and she was absolutely thrilled as well. But I think I ran around my house for like 10 minutes because I simply couldn't believe it. It was after finals in spring 2023. And so I was at home, and I think my dog, most of all, was most confused because she was like, what is going on?
Well, hey, let's talk about the specifics of your research project. What is the context of the problem that you propose to study on the Webb telescope?
Yeah, so I guess in a broad sense, we're addressing this question of massive star formation. That's sort of the central justification of it. And like I said, it's very important, but we don't still fully understand how massive stars form. So there's this open discrepancy there. There's different theories for how they form, and they need to be tested. One of the important places we do test them are in extreme environments. For example, the center of the Milky Way. It's a region called the galactic center. It's really extreme. There's high density, pressure, turbulence, that sort of thing. And so it's a key testing ground for these theories.
So you're going to point the telescope to this galactic center.
Right. So our idea was, well, let's point the Webb telescope towards one massive star-forming region in the galactic center, take data on it, and see what that might be able to tell us about how massive star formation is occurring, and importantly, how it might be occurring differently because of the conditions of the galactic center.
Got it. Now, what do you hope to discover?
We have some indications, actually, that the massive star that's forming in this region may be doing so in an isolated sense. So it may be doing it alone. And that's actually a very key distinction between different theories. So if we can confirm that this massive star is forming alone or in isolation, that would have very important consequences for our total understanding of massive star formation.
So this massive star, people have observed it in the process of being formed, and you want to go back to that region, collect more data to test your theory.
Right. So the particular region that we're studying has had some studies on it previously that seem to be very exciting for what we might learn about it. In particular, there was a paper that came out a couple years ago that showed that there may be a massive star forming in this region in isolation, so alone. And that's an important distinction to make between theories of massive star formation, is whether we see massive stars forming entirely alone or surrounded by other stuff, so other forming stars and things like that. So with the Webb telescope, we want to peer in, see, is it forming alone? If it is, how can we characterize its surroundings? So can we understand how it's forming, what are the consequences of that, and how its formation might be different in the galactic center?
So to understand how the research works, this telescope has to be pointed in the direction of the region that you wish to study. When the telescope is pointed in that direction, do you get, a few days of operational observations? How does that work?
basically for the principal investigator, that being me, it's an entirely hands-off process. So we were allocated 4 hours of
4
spacecraft
hours.
time. Yeah, just 4 hours. But the observers on the front end
Yeah.
are doing that work. So at the Space Telescope Science Institute, they're doing that work, pointing the telescope, taking the data. I don't really do anything.
Are you there in the room with them excitedly, or are you at home waiting for an email saying, here's the data?
Actually, I was at a football game.
So you're at a football game while the telescope is doing the work.
Yeah,
Okay.
and I was there. I was sitting with my girlfriend, and I looked up at the sky, and I'm like, well, there should be a big...
I hope it's working.
Yeah, there should be a big telescope a million miles away that hopefully will be taking data right now, which wasn't a guarantee. Actually, the observations had failed once in August, and they were being redone in September. And that's the time they actually went through. So I thought, well, hopefully it actually works this time.
When it failed, are you saying that there was an instrumentational failure, or?
Yeah, so there was a basic calibration that had to be made that basically failed, and they said, okay, we need to reschedule these to September 22nd, which is when they happened. It happened to be on a football game day.
Well, that's great. I had no idea that the research works that way. So now that the data has been collected, you're going to do the work and analyze it. Based on your findings, after you release them, how do you think your work will be applied in the future, say in the future of astronomy?
Yeah, so I think that it has the potential to have some important consequences for different areas of astronomy, not just star formation. In particular, like I mentioned, the galactic center is a very important and unique region, and that it's the center of our galaxy. So it's close enough that we can study it in a lot of detail, but it's also an important parallel to other centers of other galaxies throughout the universe. So people say that the galactic center is like an important Rosetta Stone for translating the local universe to the distant universe. So the more extreme, earlier universe are the centers of other galaxies. So I think if we can understand how stars and how massive stars are forming in the galactic center, it can inform a lot of our understanding even back to the early universe and the very first galaxies and the very first stars.
Got it. So you're the principal investigator. I think we need to talk about what that means. You presumably have a team of researchers working with you. What does that look like? Are there some of your professors that are actually part of your team?
Yes, so it is quite a unique position, being a student and a principal investigator. So I wouldn't say...
Basically never happened. Yeah.
Yeah, basically, yeah, never happened before, right? So I still work very closely with my advisors, and I still call them my advisors because even though I'm the PI in name, of course, I still need the expertise and the knowledge that they have to do the research and to do it correctly. But I think that I do still have final say on things that pertain to the program. So actually how we're going to proceed with the science or how we want to lay out the papers we publish, things like that. And I do plan to oversee, we want to publish a few papers on this, how those papers will proceed and what the science is that we want to do with them.
Is that awkward in any way? Is it awkward to be leading a project overseeing graduate students and faculty? What's that like?
Well, it's not awkward in the sense of I've worked a lot with these advisors previously on previous work, so I already know them. I have a solid rapport with them. But I think it is awkward in the sense of I have this responsibility as the principal investigator, but I may also have to defer to other people that have more knowledge and more expertise. So I think it's sort of a call and response. It's like working with colleagues more than it's like being a student at times. It feels like, because I have some knowledge and some expertise, they have ideas, and we exchange them and we collaborate to do good science. I mean that's how science works, right?
That's right. So you're a third year at UVA. What are your plans for the future after you graduate with your degrees in astronomy, physics, and history? Given your many interests, what's next? Graduate school in physics, astronomy, maybe history? What do you want to become?
So I think I will certainly be pursuing some sort of postgraduate study, likely a PhD program in astronomy, and of course something like a James Webb program will help set me up for that very well. Though I may also want to pursue other things. So, for example, I love the liberal arts. That's why I'm studying history, and I would like to find a way to incorporate the two. So maybe I'll pursue law school or something like that. I'm not entirely sure yet, but I would like to have a career that is both science and liberal arts in some capacity.
Well, that's great. Do you have a favorite science communicator? I know that's kind of out there, but, are you a future Neil deGrasse Tyson? Great communicator. He knows a lot of history.
Well, I think that Neil deGrasse Tyson is a very great example of someone who's very well-spoken and someone who does a wonderful job of communicating the science in a way that's digestible to the general public. So I do take a lot of inspiration from that, and I would hope that I can be something like that, either through the press on this James Webb program or in other ways, just to be someone who can be a representative and an advocate for science and to allow people to appreciate it.
So, Sam, you've done a lot of work academically here at the University of Virginia. We talked about that. But a parting thought, is there something you would like to mention about your time here at the University of Virginia? Have you participated in any clubs or activities that have enriched your experience, things that you'll never forget?
Yes, actually. So I'd say the most important is right now I'm the president of the astronomy club.
Oh, you're the president. Okay.
So I do a lot of outreach with the club, and also I just get to interact with so many people and to appreciate astronomy and to in turn help other people appreciate astronomy. In particular, if I could advertise, we're doing a trip to Zanesfield, Ohio for the April 8th total solar eclipse. We'll be in the path of totality for 4 minutes.
You're going to have totality for 4 minutes.
4 minutes, yeah. So we're bringing around 40 students, UVA students, astronomy club members, to Ohio to view this total solar eclipse. So it's this giant undertaking. We're going to do an outreach event and help people, local people, appreciate astronomy and things like that.
And you'll be bringing boxes full of the special glasses?
So we'll be bringing eclipse viewers,
Yeah.
like you say, also telescopes equipped with solar filters, so you can look directly at the sun through telescopes, and all sorts of things and demonstrations to help people, and little kids especially, appreciate astronomy and to do things like asteroid demonstrations or coloring demonstrations and things like that.
I hope for good weather for all of you. No cloud cover.
I certainly hope so too.
Well, Sam, this has been super fun. Your future career as an astronomer or perhaps historian or perhaps lawyer or science communicator, I am fairly confident you'll be successful in whatever you choose. So, Sam, you're a great role model for UVA STEM students. You are a starry, pun intended, you are a starry example of President Ryan's vision for UVA to be great and good in all that we do. Your brave dedication to the Galactic Center, it's inspirational. Good luck with your research, and thank you for being on the show. I'm Ken Ono, STEM advisor to the Provost, and Marvin Rosenblum, Professor of Mathematics, and you've been listening to Who's in STEM.
Who's in STEM is a production of WTJU 91.1 FM and the Office of the Provost at the University of Virginia. Who's in STEM is produced by Catherine Kossaboom, Claire Curzan, Ria Verma, Mary Garner-McGee, and Ariane Ballou. Our music is composed and performed by Robert Schneider and John Ferguson of Apples in Stereo. Follow us on Facebook, Instagram, and Twitter. Listen and subscribe to Who's in STEM on Apple Podcasts, Spotify, or wherever you get your podcasts. We'll be back soon with another conversation about scientific and technological innovation at the University of Virginia.